Welcome to this video on electron configurations. And if you've watched the video on orbitals, you know that we can describe the location of electrons within atoms in terms of probability density distributions, and those probability density distributions are described in terms of things called orbitals. What we're going to do in this video is actually learn how to describe where all of the electrons in individual atoms where they reside in terms of orbitals. So which kind of orbitals, what energy level of orbitals, etc., etc. And so here we've got the standard periodic table, which you should know pretty well by now. And we're actually going to make some new divisions, and we're going to create something called blocks. And so first I'm going to draw them for you. Here we've got the S block, these two families right here. Here we've got the P block. Over here with the transition metals, we've got the D block, and the lanthanides and actinides are the F block. What do these blocks mean? Well, the blocks represent the kind of orbital which contains that particular element's valence electrons. So let me write that for you here. Blocks represent location of valence electrons. Location of valence electrons. So the outermost electrons in the S block hang out in S orbitals. The outermost electrons in transition metals hang out in D orbitals. You get the picture for P block and F block. But of course, we want to describe where all the electrons hang out, not just the valence electrons. And to do that, we're actually just going to dive into a few examples. And the first example is helium. And so I'm going to write the electron configuration for helium right here, and we're going to see what we can learn about it, see if we can develop any patterns. So the electron configuration for helium is 1s2. 1s2. I should note that even though I put helium in the P block, helium is sort of not in the P block. I apologize, but it's one of the small inconsistencies in the periodic table. So 1s2. Well, this 1 right here, this represents what we call the principal quantum number of an orbital. And it really just relates the energy level. The average distance between electrons in the nucleus increases as the principal quantum number increases, and therefore the electrons have more energy. And what we can do to figure out which principal quantum numbers correspond with different kinds of elements, or different kinds of outermost orbitals, we can just label the periodic table like this. So the valence electrons in potassium, for instance, are going to be in the 4s orbital because this period has a principal quantum number of 4, etc., etc. So that's what that initial coefficient means. This S here, this S represents the type of orbital we have, the shape of the electron density distribution, and you can review those by watching the orbital video. And this superscript of 2 up here represents the number of electrons in that orbital. So in the case of helium, we've got 2 electrons to balance the 2 protons, and both of those electrons hang out in the 1s orbital. In fact, s orbitals can hold a maximum of 2 electrons, so you'll never see more than 2 electrons in an s orbital. Alright, let's move up 1 proton and check out lithium. So lithium is over here on the 2 level, and so this is what lithium's electron configuration is going to look like. It's going to be 1s2, so it's going to have the same initial configuration as helium, and then its valence electron is going to hang out in the 2s orbital, and there's going to be 1 electron there. So you can see that as we move up, we retain the electron configurations of elements behind, so to speak, the element in question, and then we add valence electrons to the s orbital, in the case of the s block, and the coefficient, the principal quantum number, corresponds just to the period which we're working with. So this is the 1 period, the 2 period, etc., etc. Alrighty, let's up the ante a little bit and check out the P block. elements in the p block. Let's start with boron. So boron is here on the periodic table within the p block. This is the electron configuration for boron. We've got 1s2, 2s2, 2p1. Let's try and relate this again to our understanding of orbitals. Boron, of course, is one after beryllium. Beryllium has a complete 1s orbital because it's got the same electron configuration in the core as helium. It's got a complete 2s orbital, and then its final electron goes in the 2p orbital. So you can see that the p orbitals begin at the 2 principal quantum number because helium is not in the p block, and so we add boron's final electron to the 2p orbital. And so you can see that the way we assign quantum numbers for p orbitals is the same as the way we assign them for s orbitals. It's just the number, the period we're working with. And we'll see this trend continue with neon. Neon has an electron configuration of 1s2, 2s2, 2p6. So neon is all the way on the right-hand side of the periodic table over here. So it's actually got a completely filled p orbital. And so we can surmise from this electron configuration here that the p orbital can hold a maximum of 6 electrons. So p orbital can hold max of 6 electrons as opposed to the s orbital, which can hold 2. Alright, let's up the ante even further, and let's go to scandium, a transition metal. In fact, this example is going to be scandalous. Alrighty, so scandium hangs out right about here, and this is going to be a little bit of a monster, but I'll write out the entire electron configuration for scandium for you right now. It's going to look like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Alrighty, so let's look at this part right here, everything before the 3d1. This part should really make sense if you've understood these original examples. If scandium is right here, everything except that final electron is going to be the same. They're going to hang out in the same places for which they hung out in calcium. And so we're going to fill the 1s orbital, we're going to fill the 2s orbital, we're going to fill the 2p orbital here with 6 electrons, 3s orbital with 2, 3p with 6, and 4s with 2. Now we've got one extra electron, and of course this scandium is a transition metal, so it's going to hang out in the d block. And so we're going to add an electron, that final electron, to a d orbital. The question is, why do we have a 3 instead of a 4 in front of our d? And that's just the way electrons are distributed in the d orbital. Instead of taking an energy level of n, d orbitals, or d energy levels, are described by n minus 1. So we take the period which we're working with, in this case this is period 4, and the first d orbital we're going to work with is not going to be the 4d orbital, it's going to be the 3d orbital. Similarly, at period 5, valence electrons for these transition metals right here, these are going to hang out in the not the 5d orbital, but the 4d orbital. So d is always n minus 1. Now let's change things up here. Let's take a look at the electron configuration for zinc, but we're going to look at it in a slightly different way. Instead of sort of cumbersomely writing out all of these orbitals, all of these electron configurations, we're just going to say that, well, zinc is over here. It has effectively all the same electrons, for the most part, as argon, all the same inner electrons as argon, and so we can represent that by doing something like this. Writing this just represents the complete electron configuration for argon. So this is the complete argon configuration. It's sort of a shorthand way of representing all of the lower level orbitals. And then we can just write the valence electrons. So the valence electrons for zinc, they're going to be 2 in the 4s orbital and 10 in the 3d orbital, because zinc is the 10th transition metal in that period. So the electron configuration for zinc is going to look like argon, 4s2, 3d, 10. And that makes sense again. And one final thing to note about the D block here is, as I said, zinc is the final transition metal in that series. Since it has 10 electrons, we see that d orbitals can hold a max of 10 electrons. So d orbital can hold 10 electrons. So to summarize, s orbitals can hold 2 electrons, p orbitals can hold 6, and d orbitals can hold 10. And as another final note, I've made a few final notes, but these electrons here that are not valence electrons within this argon configuration, this is either called the noble gas configuration, and we can also call these core electrons. So electrons that don't hang out in the highest energy level, these are called core electrons. Now that we've done a bunch of examples, let's sort of summarize some steps. So when you get a problem on your test that says determine the electron configuration for some random element, you'll have some steps to work with that you can remember. The first thing to do is determine the nearest noble gas configuration. So whenever we're given an element, we're going to work sort of backwards and say, what's the largest noble gas that's smaller, that has fewer protons than our element? So in the case of zinc, that was argon. Maybe in the case of sulfur, that's neon, etc., etc. And instead of writing out sort of cumbersomely all the inner electrons and core electrons, we're just going to write the noble gas configuration like we did here for zinc. That's the first step. The second step is to move left to right and fill in the orbitals, the ns orbitals, so using the n quantum number for s, and the np orbitals, remembering that s orbitals can hold a max of 2 electrons, and p orbitals can hold a max of 6 electrons. If we've got a transition metal, first we fill the ns orbital, and then we fill the n-1d orbital, noting that d orbitals can hold a maximum of 10 electrons. So now we've got even more examples, and I want you to take a look at these on your own. So pause this video, get out your periodic table, and see if you can figure out the electron configuration of bromine. Alrighty, welcome back. Let's see how you fared with question 1. So if we follow our steps here, the first thing we're going to do to figure out the electron configuration of bromine is figure out the nearest noble gas. And if we go up here, locate bromine, that's over here. The biggest noble gas that's smaller than bromine is argon. So our noble gas configuration for bromine is going to be argon. Let's see, bromine is in the 4 quantum level, I believe. Yep, that's right, 4 quantum level. So we're going to fill the 4s2 orbital, and we're going to have 5 electrons in the 4p orbital. So the electron configuration for bromine is argon, 4s2, 4p5. Alrighty, let's try something a little bit different. I want you to locate the atom with an electron configuration of krypton, so this is our noble gas configuration, 5s2, 4d3. So a completely filled 5s orbital and a 4d orbital with 3 electrons. Pause this video, get out your periodic table, and give it a try. Alright, welcome back again. Let's see how you did. So let's see, we're going to look at the 5th period on the periodic table, because remember, this is n, and this is n-1, so we're looking at the 5th period, and we're looking at the 3rd transition metal in the 5th period, because we've got 3 electrons in our d orbital. So what's the 3rd transition metal in the 5th period? Well, that's Nb. I'm actually not even sure what that stands for. It's embarrassing, but no matter. So the atom of the electron configuration of krypton 5s243 is Nb. Let me just look that up. I can't. Let's see. That's niobium. Niobium, the incredibly unpopular element, niobium. Alright, now here's a slightly trick question. I want you to find the electron configuration of an oxygen anion, so with a charge of 1-. See if you can do that. Welcome back for the third and final time. Let's tackle this problem together. And this is a little bit different because we're not just finding the electron configuration of oxygen, we're actually figuring out the electron configuration of an ion. But if we think about what an ion is, this problem really shouldn't be too difficult. An ion, when we have a charge of 1 minus, just means we have an atom plus 1 electron, because electrons have charges of -1. So what we're going to do is we're going to find the electron configuration of oxygen and then add 1 electron to it. So the electron configuration of oxygen is a pretty small element relatively. So our noble gas is going to be helium. It's in the second period, so we're going to fill the 2s orbital with 2 electrons. We're going to fill the 2p orbital with 4 electrons. So the electron configuration of oxygen is going to be helium, 2s2, 2p4. And then because this is an anion with 1 extra electron, we're just going to add 1 electron, and we have no choice but to add that to the 2p orbital because our 2s orbital is filled. So the answer to this question is helium, 2s2, 2p5. So we've done a bunch of examples here, but the thing to remember is whenever you're confronted with an electron configuration problem, go back to your periodic table, find that element in the periodic table, identify the nearest noble gas, move left to right, filling in the s orbitals and the p orbitals if your element is in the s block or the p block, and if your element is in the transition metal, just remember that the principal quantum number for your d orbital isn't going to be n, it's going to be n-1. But in these kind of questions, the periodic table is most definitely your best friend. Thank you very much, and I will see you in the next video.